Art Edison, and I'm a professor at the University of Georgia. I also direct the NMR facility in the Complex Carbohydrate Research Center at UGA. I have taught introductory NMR to biologists and biomedical scientists for over 25 years. I've been frustrated by the lack of material in this area that is dedicated to non-experts so that they can understand the basics and use this powerful technology to solve biological applications. It is true that if you want to develop new NMR methods, you really do need advanced training in topics like quantum mechanics, physics, analytical chemistry, programming, et cetera, et cetera. There are a lot of resources for these that are directed towards the experts. There are not as many resources, in my opinion, directed toward non-experts to try to give you some idea about how you can use this technology. This video is the first in what I hope to be a series that will introduce non-NMR experts into this technology so that you can do exciting research with it. This concept is at the heart of the Network for Advanced NMR, NAN, which is funded by the National Science Foundation. UGA is partnered with the University of Connecticut, University of Wisconsin at Madison, to develop an NMR instrumentation network as well as knowledge bases to help users find resources and apply them to solve their problems. This first simple video introduces the basic concepts, the magnet, the sample, and how they interact. I hope that you enjoy it. What do you think about when you think about a magnet? Perhaps a refrigerator magnet, or a magnet that was used to make shapes in iron filings when you were a kid. Well, we also live in a magnet. The Earth is a big magnet. Its field strength varies over time and location, but it averages around half a Gauss. This is enough to protect us from lots of solar particles and radiation that would eliminate life on Earth if it weren't there. It also allows us to navigate through compasses that point to the North Pole. There are some other interesting things that you can do with the Earth's magnetic field. In fact, here's a really neat example of helicopter-borne NMR from the folks at Albuquerque Magnetic Resonance, where they used the Earth's magnetic field, and then the rest of the system was put into a device that could be carried by a helicopter, and then they could search for oil under ice, under Arctic ice to see oil spills. So very ingenious application of Earth's magnetic field for NMR. How do you make a magnet? Well, a lot of you, when you weren't doing iron filings, perhaps were making magnets by wrapping copper wires around nails. If you take a copper wire and make a solenoid around a nail, just like shown in this drawing, and attach one end to the positive pole of a battery and the other end to the negative pole of the battery, you got to be careful. This gets hot. So, and actually, if you look in this link, or just Google making electromagnets, you'll find some nice ways of doing this where you won't always burn yourself. If you connect the wire to the battery, it'll create a current, which then in turn creates a magnetic field along the axis of the nail. That nail becomes a magnet. You can pick things up like paper clips. And then as soon as you let go of that wire, then the magnetic field stops. Turns out that an NMR magnet is very similar to that copper wire wound around a nail. A little bit more complicated in practice and implementation, but the same general principle. In NMR, we have these big cans that are really thermoses, or called cryostats, that are designed to hold, in this case, liquid nitrogen is on the outside in this nice cutaway that I found at JEOL. Liquid nitrogen is on the outside. It's stored at, it's at 77 degrees Kelvin. It keeps liquid helium on the inside cold at 4.2 degrees Kelvin. And then the liquid helium bathes coils that are a lot like that coil of wire going around a nail, And these are superconducting coils in the center of the magnet. Once magnet technicians bring the magnet up to field, engineers bring it to field after it's cooled down and put current into there, then this creates a magnetic field along the vertical axis of this magnet in here. You have to be careful if you work around these things, because the superconducting magnets are always turned on unless they're deliberately turned off or they quench, which is not something that we want to have happen. And so you have to be careful. You also have to be careful if you're an MRI technician or working in a hospital, a healthcare setting that has an MRI system. These things are always turned on. So how strong is the magnetic field? Well, magnetic resonance imaging is really the same physics as NMR, but the magnet is turned horizontal so that people can get in there. Typical magnet strength for MRI is 1.5 Tesla, which is 15,000 Gauss. That's pretty strong compared to the Earth's magnetic field. And in the MRI system, a proton or a hydrogen atom will resonate. I'll talk a little bit more about this in a few minutes, at 63.8 megahertz. We usually use bigger magnets for nuclear magnetic resonance for chemical analysis. An NMR system, a typical NMR system, is 14.1 Tesla, for example, or 141,000 Gauss. This is over 280,000 times the strength of the Earth's magnetic field, really strong. In this system, a proton would resonate at 600 megahertz. The magnet by itself doesn't do that much. It's a nice thing. It will attract objects, but it doesn't do NMR. What we need to do NMR is to have something called the NMR probe. And there's a drawing of an NMR probe, a sample, and a spinner on the right. I'll talk more about these in a little bit. So the sample and the spinner go together like that. Here's a little bit of an expansion of the sample inside the probe, where a coil is configured in a way to produce a magnetic field that's perpendicular to the main axis of the magnet. And when that happens, and that probe is put into the center of the magnetic field, then you get what's shown above. You get the main magnetic field pointing along the axis of the magnet, and then a perpendicular magnetic field pointing that interacts with the sample. And with this, you can do NMR. So let's think about what happens when we put a sample into a magnet with a probe like this. First of all, sample preparation is a big topic and will not be covered here. In subsequent videos or a lot of other reference material, you might find some more information. For a lot of the applications that we are going to talk about in this series of lectures, you would use a 5 millimeter NMR tube. This is a little bit narrower than most pencils. You fill it up with about 600 microliters of a solution of liquid. It is possible, in fact, becoming very popular, to do NMR on solids, but that's not what we're talking about here. This is for liquid NMR. So here's a photo of a sample tube filled with a liquid on the bottom and being held in what's called a spinner, which holds that in the magnet, like I showed you on the previous schematic. You get the right depth of the sample by using something called a depth gauge. So shown here with the solid line in the center is where that sample is going to be positioned in the magnetic field. That's right in the center of the coils of the probe. When we're doing things like metabolomics or screening for ligands in NMR, we can use automation. And in this case, we could not just use one tube at a time, but we can put in a rack of, in this case, 96 tubes at a time, which makes automation work. And then there's a sample changer that you can purchase and install on the top of your magnet that will then allow you to go through and collect NMR data on each of these tubes individually. So what happens when you get a sample? You put it in, you position it correctly, you put it into the magnet, you drop it down. What do you get? Well, here's one of the simplest molecules, water. Water has two hydrogen atoms shown by the white spheres. We call them protons most of the time in NMR, because what we're really concerned about is the nucleus of NMR. That's the nuclear part of nuclear magnetic resonance. Let's consider the nucleus of that particular atom. Well, when the nucleus has a magnetic moment, and when you put that water molecule or a lot of water molecules in the tube into a magnetic field, then that magnetic moment will interact with the magnetic field much in the same way that a bar magnet would interact with a magnetic field. So you can, in the simplest description of NMR, we can talk about the nuclei as behaving like little bar magnets. It's actually more complicated than that, and I'll start to cover more complicated variations of this theme in later videos. But this works for right now, and it actually is a pretty good description. So you put your sample into the magnet, you have a bar magnet, it aligns with the magnetic field, then what happens? Well, when you put that sample into the magnetic field, those bar magnets start to behave like a gyroscope moving in the Earth's gravitational field. The same equations of motion that describe this gyroscope, which is spinning along the axis that is going around. So it's spinning along the center axis, and then that creates a force pushing it up. Gravity has a force pulling it down, and the net result is this thing called precessional motion, in which the gyroscope goes around and around and around. The precessional motion of a nucleus is proportional to the magnetic field strength. So at 600 megahertz, at a 14.1 Tesla magnet rather, a proton will resonate at 600 megahertz. When that happens, that nucleus generates a signal, like this one that was collected on a water sample or a D2O sample in a 600 megahertz magnetic field with an offset of about 100 hertz. So under this condition, that nucleus is this is representing the spinning around inside the coil that was exactly the same as we saw for the gyroscope in the little video just now. This also decays over time. We'll talk more about that over time in subsequent lectures, and that decay will be useful in many cases. And the important thing here is that this only happens at the correct frequency. So you have to put in exactly the right frequency through this coil. In this case, 600 megahertz will excite that resonance and we'll get it going. Other frequencies don't do it. So that's the resonance part of nuclear magnetic resonance. We can look at this signal and say, well, we could probably even analyze that with a simple case of just water in a magnetic field. But what we normally do is something called the Fourier transform. This is the same data as shown here. So this is collected over time in this free induction decay. And then we can take the same data and transfer it to the frequency domain, where in this case, we just have one peak. And we typically, by custom, we put that at 4.7 parts per million to reference everything about right. So this is the water resonance in a D2O sample, residual water, and it shows up as just one peak in an NMR spectrum. This is a free induction decay, the same kind of data. In this case, it's from human urine, so much more complex sample than D2O, and or the residual water in D2O, I should say. So in this case, it's the same kind of thing, but it's a more complicated because there are more signals. So we collect this in this case for 3.6 seconds in the example shown here. This is what it looks like at the start of this FID. It's a much more complicated signal than the simple sine wave that's generated by the H2O. And this has the contributions of all of the different nuclei in the sample at once. That seems complicated. It is much more complicated than a simple sample, but the concept itself is pretty familiar to anyone who has listened to a record. And here is a picture of a phonograph, of a record, a vinyl record. And the record has grooves, which the needle or the cartridge in the will track along when the record is turning around. And the cartridge tracks the record grooves, much like the signal that we see from this free induction decay. And so the point here is that you can actually, with a single groove on a record, you can represent what a Beethoven symphony, or in this case, a Bach unaccompanied violin sonata, or you could have a recording of your favorite rock and roll band. But they're all a single complicated waveform that you can listen to, or you can see here. So just like the water, we do a Fourier transform of this urine spectrum, and this is what we get. In this case, there are many more peaks than just residual water. In fact, we've taken the water out of this signal so that we could see the rest of the sample. There are a lot more peaks in here, and subsequent videos will tell more about how to think about this, how to interpret this, and what it means. I hope that you enjoyed this video and that you stay tuned for future ones in this series. Thank you.